All right, class, so this is another ideal gas law problem, and this time we're going to be using stoichiometry. So it'd be a stoichiometry plus ideal gas law type problem, and this is a pretty basic one. So what we're asked to do here is basically what we're looking for is the volume of O2. So as we're getting this problem, the volume of O2, that's our question, basically, that's what we're trying to figure out. Required for the complete combustion, so this is going to be sort of a stoichiometric relationship, and we're going to react all of this acetylene. And it tells us assume that the temperature and pressure are the same for each gas. So it doesn't give us a specific temperature and pressure. You can assume a temperature and pressure. You can set, let's just use STP for example. If you wanted to, you don't need to though, and I'm going to sort of show you how to get around that. So the first thing we're going to need to do is balance this chemical equation. So here I've got these little spaces, right? And that's going to indicate to us that I want you to balance it. But even if I don't put those there, even if you don't see, you should always double check to make sure that you have a balanced chemical equation. So in order to balance this, I know that just filling these in here, if I didn't know this information, I'd probably put a 2 here first for the carbons, and then sort of balance the oxygens as well. But I know that this is how to balance this properly. If you need help balancing chemical equations, definitely you can check out a different video, or let me know, and I will help you with that. And I've got this amount of acetylene. So at this point in time, what I would start to think about essentially is what is the ideal gas law, and what sort of conclusions or what can we sort of figure out essentially in order to help us solve this problem. So PV equals an RT. I know that the pressure and the RT part are going to stay constant. So I like underlining these things to sort of indicate the pressure and RT will stay constant. I could rearrange this to have volume over N over our number of moles equals RT over P. And all of this is going to equal a constant, right? That's going to be the same for acetylene, for oxygen. That will always be the same. That will always be constant. So this is really Avogadro's law. And even though we're using two different gases, their volume to number of moles relationship is going to be exactly the same. It doesn't matter that one is acetylene and one is oxygen, and this is a sort of a different treatment of this. We don't know exactly how many moles we have because we don't know the actual temperature and pressure, but that's okay. We don't need that information to solve this problem. So this is a derivation essentially of Avogadro's law, and what I can do then is I can say, well, if I have 7.64 liters of acetylene and I divide that by the 2 moles here. So I'm just going to say, well, let's assume that we've got 2 moles and 5 moles. That will help us solve this problem. And that will equal a constant. And that constant, because we're at constant temperature and pressure, will be relatable to the oxygen as well. So for oxygen, I don't know how many liters I have, so I'm going to put X liters. And I know that will be a 5 mole ratio. So it's a 2 to 5 mole to mole ratio. And then my liters, right, this is just basically going to be the same sort of ratio if both gases are the same temperature and pressure. So now I solve for X, and X equals 19.1 liters of oxygen, and that's my answer. That's all I really need to do. Now alternatively, you could do this problem by solving for a certain number of moles of acetylene. That's totally valid. And the temperature and pressure that I would recommend using in that case would just be STP. Just use standard temperature and pressure, 273 Kelvin and 1 atmosphere. Then you'll be able to solve for some certain amount of moles of acetylene. Then you use the mole to mole ratio and then plug that back in to solve for the volume of oxygen. So once you have a moles of oxygen, you could solve for the volume of oxygen, again, using the same temperature and pressure, and you should get essentially the same answer. Depending on how you round, it might be a little bit different, but it should get you to essentially the same answer. So it really doesn't matter what the temperature and pressure is. This relationship of V over N should stay constant, no matter the gas. So as long as we are using this as a constant, we can just do this simpler treatment and get 19.1 liters as our volume of oxygen. All right, I hope that makes sense. If it doesn't, definitely let me know. And thanks a lot.